Hello, this is Richard Hammack's Calculus 1 course. We are in part 1 of the course, a function review. Today's lecture is our first installment of a trigonometry review. Trigonometric functions are very useful functions that will play a big role in calculus. The main idea is that trigonometric functions relate angles of right triangles to their side lengths. For each trigonometric function, you can think of the input as being an angle and the output as being a side length. For example, consider this right triangle whose hypotenuse is 1. Imagine we have an angle theta situated here. And think about theta as being a variable, so that angle can open up like a hinge. And as it opens up, the opposite side length changes. As the angle theta gets bigger, you'd expect this side length, this vertical side length, to get bigger as well. So that vertical side length is a length y that depends on theta. And it turns out, as you may know, that in this case, y is equal to sine of theta. Sine, the trigonometric function sine, is the function that tells you the length of this vertical side of the triangle in terms of the angle theta. Today's plan is to, first of all, discuss the system of radian measure, which is a very natural way of measuring angles that's used almost exclusively in calculus and higher math. Then we'll define and review the trigonometric functions sine, cosine, secant, cosecant, tangent, and cotangent. Now, you've probably studied these before. Today we will review them and look at them especially in a context that is useful for calculus. I'll try to pick up on the high points of trigonometry with an eye towards the kinds of things that you're going to be using in class. Trigonometric functions are actually very simple. They have really just two ingredients. The first ingredient is the Pythagorean theorem, which says that if you have a right triangle with legs x and y and hypotenuse z, then x squared plus y squared always equals z squared. And you're familiar with this theorem from geometry. The second ingredient is what's called the unit circle. The unit circle is the graph of the equation x squared plus y squared equals 1. It's a circle of radius 1 centered at the origin 0, 0. Now, when we say it's the graph of the equation x squared plus y squared equals 1, we mean it's the set of all points xy on the plane that satisfy that equation. Now, to see why the equation x squared plus y squared equals 1 has a graph that's the unit circle, take an arbitrary point xy on a circle of radius 1 centered at the origin. So the distance from xy to the origin is 1, as indicated here. And the x coordinate of this point xy can be thought of as a horizontal side of a triangle, and the y coordinate is the vertical side. And by the Pythagorean theorem, x squared plus y squared equals 1 squared, or x squared plus y squared equals 1. So any point xy on this circle, being a distance of 1 from the origin, has to satisfy x squared plus y squared equals 1. Conversely, if a pair xy satisfies this equation, then it's at distance 1 from the origin, so it's on the unit circle. The unit circle is a very basic object for us. Let's think about its circumference. The circumference of a circle is pi times its diameter, and the diameter of the unit circle is 2. From -1 to 1 is a distance of 2. So the unit circle has circumference 2 pi. So starting here, going all the way around the unit circle, and coming back to where you started, you've gone a distance of 2 pi units. The important thing about the unit circle is that it's a natural protractor for measuring angles. To illustrate this, think about an angle, theta, as indicated here. If you wanted to measure this angle in the old-fashioned way, you might take a protractor, plop it down so its center is right there at the vertex of the angle, and you'd measure off and you'd say, well, this angle has a degree measurement of 45 degrees. Theta is 45 degrees. Now that's fine, but a protractor is a man-made device that is somewhat arbitrary in its markings. Why is a right angle 90 degrees, you might wonder? Why is there 360 degrees around a circle? One reason is that a lot of numbers divide evenly into 360, perhaps. But nonetheless, it's sort of arbitrary. Radian measure, by contrast, is going to measure this angle by the unit circle. Let's take that exact same angle theta, and this time, rather than the protractor, let's put the unit circle centered right at its vertex. So the way we're going to measure this angle on the unit circle is we simply measure the distance from this point along the unit circle to this point. Now, the total distance around this unit circle is, we said, 2 pi. It's a length of 2 pi, that's its circumference. And 45 degrees is 1/8 of 360 degrees. So the distance from here to there would be 1/8 of 2 pi, or 2 pi over 8. And that reduces to pi over 4. So we're going to take that arc length as a measurement of this angle. It's called the radian measure of this angle. We say the angle has radian measure, theta equals pi over 4. So the unit circle is a very natural protractor. It's a part of nature. In calculus, although you sometimes refer to angles by their degree measurements, ultimately you think about them as measured in terms of radians. So let's think about radian measure. Here's the unit circle. And I'm going to divide up the unit circle in a couple of ways. Let's divide it up in pi slices of 45 degrees into 8 equal parts. This point right here, we would say that's 0 radians. And as you move counterclockwise along the circle, the radian measure increases. And we said a 45-degree angle would be a distance of pi over 4. So there it is. That's pi over 4 radians, marking off 45 degrees. If we double 45 degrees to get 90 degrees, that radian measure would double as well. You'd get 2 times pi over 4, which is pi over 2. So 90 degrees is pi over 2 radians. If you did 4 times pi over, or 3 times pi over 4, that's going to take you to 3 pi over 4 radians. And that's, what, 135 degrees. And 4 times pi over 4 would be pi. So 180 degrees is pi radians. And that makes sense because the unit circle, we said, had a circumference of 2 pi. We're halfway around the unit circle, so we're at a radian measure of pi. Continuing this another pi over 4, we have 1, 2, 3, 4, 5 times pi over 4 radians. 6 times pi over 4 radians would reduce to 3 over 2 pi. So 3 pi over 2 is, radians is 270 degrees. Add another pi over 4, we're at 7 pi over 4. 1, 2, 3, 4, 5, 6, 7 pi over 4s. And finally, we complete the circle by going an additional pi over 4. 7 pi over 4 plus another pi over 4 is 8 pi over 4, or 2 pi. You've come all the way around the circle. Its circumference is 2 pi. 2 pi radians is the same as 360 degrees. But like degrees, you can continue. To 2 pi, add another pi over 4. Let's see, 2 pi was 8 pi over 4, go another pi over 4, that's 9 pi over 4. And notice that's the same point as pi over 4 on the unit circle. You've come all the way around the unit circle, you've doubled back to 9 pi over 4. Add another pi over 4, you get 10 pi over 4, which reduces to 5 pi over 2. That's right there at pi over 2. Continuing, you get 11 pi over 4 radians, and here you are at 3 pi radians. Let's see, pi, 2 pi, 3 pi. Continuing your way around the unit circle, add another pi over 4, you're at 13 pi over 4. And then 14 pi over 4, which is 7 pi over 2. And then 15 times pi over 4. And then you have 16 pi over 4s, which reduces to 4 pi. So notice that 0 radians, 2 pi radians, and 4 pi radians, they're all at the same point on the unit circle. 0 radians, you haven't gone anywhere. At 2 pi radians, you've gone around once. At 4 pi radians, you've gone around twice. 2 times 2 pi is 4 pi. And of course, this continues in this clockwise fashion forever. Let's also divide the unit circle into multiples of 30 degrees, and that's going to cut the unit circle into 12 pi slices. So here's 0 radians right there as before. Now, going from 0 radians increasing to this point at 30 degrees, that's 1/12 of all the way around the unit circle, 1/12 of 2 pi, and 1/12 times 2 pi is pi over 6. Doubling that, you get 2 times pi over 6, which reduces to pi over 3. And here's 3 times pi over 6, which reduces to pi over 2. And that's 90 degrees, just as we had here. Continuing, 4 pi over 6 reduces to 2 pi over 3. Here's 5 pi over 6. And then we have 6 pi over 6. That's 1, 2, 3, 4, 5, 6 pi over 6s. 6 times pi over 6 is pi. You're at 180 degrees. Same thing you had here. We'll go one more. Here's 7 pi over 6 radians. Now, we regard counterclockwise motion as being positive radians. Clockwise is negative radians. So starting at 0 and going backwards pi over 6, that would be a negative pi over 6. You come down like this. And here's negative 3 over pi. That's 2 times negative pi over 6. 3 times minus pi over 6 would be negative pi over 2. That's like negative 90 degrees. Here's negative 2 pi over 3. And continuing around, we get negative 5 pi over 6. Add another negative pi over 6, you get to negative pi. So negative pi is right there with pi. Pi is like 180 degrees. Negative pi would be negative 180 degrees. And this continues along in that fashion. You could go forever. Let's think more about radians. Here's an angle of theta radians. So you might think that the distance from here to here is theta. The length of that is theta, so that's theta radians. Notice that at theta radians, whatever value theta is, you could be right here. You could add a 2 pi to it, go all the way around the unit circle, and you're back where you started. You're at theta plus 2 pi. You took one lap around the unit circle. Now from theta plus 2 pi, go another 2 pi, and you're at theta plus 4 pi, and then another 2 pi around unit circle, another lap around the circle would put you at theta plus 6 pi, and so on. In general, if you take theta plus k times 2 pi, where k is a positive integer, you've started at theta and you've taken k laps around the unit circle, getting right back to where you started. So all of these different radian measures that are listed here, this infinite list, they're at the same point on the unit circle, but they're different radians. On the other hand, from theta, you could go backwards, negative 2 pi, taking one lap around the circle backwards to get to theta minus 2 pi. And you could keep going around backwards, taking laps around the unit circle, theta minus 4 pi, theta minus 6 pi, and in general, theta minus k times 2 pi. You're taking k laps around the unit circle backwards. All of these different numbers, there are infinitely many numbers here, they represent the same point on the unit circle, although they're different radian measures. And this happens, again, because you can go around the unit circle as many times as you want to. So to summarize, what we have here is that any angle theta on the unit circle is at the same point as is theta plus k times 2 pi, where k is an integer. Let's summarize that. If a point on the unit circle is at theta radians, then this point is also at theta plus k times 2 pi radians for k equals 0, or plus or minus 1, or plus or minus 2, or plus or minus 3, and so on. Sometimes you'll have to convert between radians and degrees. Often you'll be able to look at an angle, like you'll get used to this, for example, pi over 4, you'll just know that's 90 degrees, and you'll know 90 degrees is pi over 4 radians. But sometimes it's not quite so obvious, and you'll need to convert. And converting is really easy, and I recommend that you don't remember any formulas for this because you can just figure it out. Here's an angle, let's say it's deg degrees and rad radians. And the way to switch back and forth between deg and rad is the following. Think about a straight angle. It's 180 degrees, or pi radians. Now this angle, deg, is a certain fraction of 180. This angle, rad, is a certain fraction of pi, and those fractions are the same proportion. So we get this equation, deg is to 180 as rad is to pi. And you can solve that two ways. On one hand, you can multiply both sides by 180 to isolate the degrees. Deg equals rad times 180 over pi. Just multiply both sides of this equation by 180. On the other hand, solving the other way to isolate rad, multiply both sides of this equation by pi, and you get rad equals deg times pi over 180. And these formulas allow you to switch back and forth between radians and degrees. So as an example, let's convert 75 degrees to radians. So we want to use this equation that gives us rad in terms of degrees. You would just take this 75 degrees and plug it in for deg right here. Solution, rad, is 75 times pi over 180. And that reduces to 5 pi over 12. So 75 degrees is 5 pi over 12 radians. Let's convert 60 degrees to radians. Now here, from the previous slide, you probably already can see that 60 degrees is pi over 3 radians, just from your mental image of the unit circle. And if you're not there, you'll get there very soon, just from working with these things. But let's double check that. Using this formula, rad would be 60 degrees times pi over 180, the same formula we used back here, and that reduces to pi over 3, as we already knew. Now we can define functions sine and cosine, now that we understand radian measure. Sine and cosine are the two most basic trigonometric functions. And we'll define them in this box. In each case, the input is a radian measure theta, and the output is the side length of a certain triangle. So for an input theta, we're going to define sine of theta and cosine of theta. And these trigonometric functions come from the unit circle. So let's draw that unit circle. Let's put theta on the unit circle. So whatever theta was plugged into these functions, you go a distance counterclockwise theta to a point P on the unit circle. And here's what you do. Sine and cosine are going to come from this point P at theta radians. Sine of theta is going to be the y-coordinate of this point P. Sine of theta is the y-coordinate of P. It's this distance right here. And cosine is the x-coordinate of the point P that's at theta radians. Cosine theta is the x-coordinate of the point P. So you can see here, cosine theta and sine theta are side lengths of this right triangle right here, whose hypotenuse is 1. Let's look at some examples. We're going to plug in certain elemental radian values into sine and cosine here. Radian values that are multiples of pi over 2, multiples of 90 degrees. Let's start with a radian measure of 0. And let's work out cosine of 0. So that's cosine of this radian measure 0. It's going to be the x-coordinate of the point P at 0 radians. And this point right here, you can see it has x-coordinate 1. So that means cosine of 0 is equal to 1. What about sine of 0? That's the y-coordinate of this point at 0 radians. And that y-coordinate is 0. So sine of 0 equals 0. Let's try pi over 2. Cosine of pi over 2 would be the x-coordinate of pi over 2. And that x-coordinate you can see is 0. But sine of pi over 2 is the y-coordinate of this point at pi over 2 radians. And that y-coordinate is 1. So sine of pi over 2 is 1. What about cosine of pi? It's the x-coordinate of the point at pi radians, and that x-coordinate is negative 1. So cosine of pi is negative 1. But the y-coordinate of this point at pi radians is 0, so sine of pi would be equal to 0. 3 pi over 2. Cosine of 3 pi over 2 is the x-coordinate of this point at 3 pi over 2 radians, and it has an x-coordinate of 0. So cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is the y-coordinate of this point, and you can see the y-coordinate is negative 1. And finally, let's go around to 2 pi. Cosine of 2 pi is the x-coordinate of the point at 2 pi radians, which is 1. Sine of 2 pi is the y-coordinate of this point, and you can see that that y-coordinate is 0. So it's really easy to calculate sine and cosine of numbers, radian values, that are multiples of pi over 2. You never need a calculator to compute them. In fact, resist the impulse to reach for your calculator when you have something like cosine of pi over 2. Think about the unit circle. If you rely too much on your calculator, you're going to forget what trig functions are. And if we forget what trig functions are, we're in trouble. We need to understand how they work and what they mean. And working out sine and cosine, as we've done here by hand, is important for that. Now, of course, you're going to have other angles that are not multiples of pi over 2, and you'll want to compute sine and cosine of them. There's some especially common angles, 45 degrees, 60 degrees, and 30 degrees. Let's talk about them. For these types of angles, you should have in mind two standard triangles. On one hand, we have what's called the 45-45-90 triangle. It's an isosceles triangle. Its two angles here are 45 degrees, and then you have a right triangle. And for the model here, think about the hypotenuse as being 1. So you can put it on the unit circle. It's got two equal legs, x and x. And to figure out what x is, if you don't already know, you can use the Pythagorean theorem. X squared plus x squared equals 1 squared. And that's 2x squared equals 1. Divide both sides by 2. X squared is a half. And now take the square root of both sides. X equals the square root of 1/2, which is 1 over square root of 2. And that's a fine answer, but you might want to rationalize the denominator. You don't have to, but let's say we'll go ahead and do it. We'd multiply that by 1 in the form of root 2 over root 2, and you get x equals the square root of 2 over 2. So the two x's that you see here, their lengths are both square root of 2 over 2. Now, having made this computation, we're going to gray out the computation, and you want to remember this triangle, the 45-45-90 triangle with side lengths square root of 2 over 2 and hypotenuse 1. Commit that to memory. There's another basic triangle that's important for us, and it comes from the equilateral triangle, 60, 60, 60 degrees for the three angles, of side length 1 on each side. And we're going to chop that right in half. So this angle up here is half of 60 now. It's 30 degrees, and this one down here is 60 degrees. And this hypotenuse remains at 1, which it started out life as. But what have we done here? This side that was 1, we've cut it in half. It's now 1/2. And then we've got this vertical side, y. Now, what is the length of that side? You can use the Pythagorean theorem from this right triangle. 1/2 squared plus y squared equals 1 squared. Now, 1/2 squared would be 1/4. Subtract 1/4 from both sides. 1 minus 1/4 is 3/4. So we get y squared is 3/4. Now take the square root of both sides. Y is the square root of 3 over 2. So this vertical side of the 60-30 triangle is square root of 3 over 2. And I'm going to gray out that computation. And now let's get rid of that half of that triangle. And we have what's known as the 30-60-90 triangle. Commit this triangle to memory. The 30-60-90 triangle has hypotenuse 1, shorter side of 1/2, and the longer side, which is adjacent to 30 degrees, is square root of 3 over 2. Now, if you remember these two triangles, and even if you forget them, you can always recalculate them with the Pythagorean theorem, as we did here. If you remember them or can work with them, then that's the key to figuring out sine and cosine of a lot of different angles. Let's take some examples. Let's work out cosine of pi over 3 and sine of pi over 3. Always we go to the unit circle. And pi over 3, remember, is 60 degrees. So if we draw a pi over 3 on the unit circle, it forms a little triangle that's a 60, 30, 90 triangle. It looks just like this one. The x side is 1/2. The y side is root 3 over 2. So cosine of pi over 3, being the x-coordinate of this point at radian measure pi over 3, is 1/2. We can read it right off the unit circle from this triangle. Sine of pi over 3 is the y-coordinate of this point at radian measure pi over 3, and it's root 3 over 2. So those trig values are got immediately from our familiarity with the 30-60-90 triangle. What if we had sine of 7 pi over 3? Let's figure out where 7 pi over 3 is. Here's pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 times pi over 3, 7 times pi over 3. It's right there, right at pi over 3. So sine of 7 pi over 3, that's going to be the y-coordinate of this point at radian measure 7 pi over 3. And again, that's the square root of 3 over 2. Let's try two more. How about cosine and sine of negative pi over 4? To work these out, the first thing you'd want to do is locate pi over 4 on the unit circle. And here it is. We'll locate negative pi over 4 on the unit circle. Here it is down here. It's a negative radian measure, so we're measuring backwards, clockwise. And we get this little 45, 45, 90 triangle. And we know that its side lengths are square root of 2 over 2. So cosine of negative pi over 4 would be the x-coordinate of this point, which would be square root of 2 over 2 from our triangle. Sine of negative pi over 4 would be the y-coordinate, square root of 2 over 2. But notice it's a negative y-coordinate, so we're going to get negative square root of 2 over 2. You see how easy it is to work out trig functions from the unit circle when you know these triangles. Let's try cosine 5 pi over 6 and sine 5 pi over 6. To do these, the first thing we'd have to do is locate 5 pi over 6. So here's pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6 is right there. And this is going to form, if you look at it, a little triangle like that. And this angle is 30 degrees. So this is a 30, 60, 90 triangle. Vertical side is 1/2. The horizontal side is square root of 3 over 2. It's like this triangle turned on its side. So cosine 5 pi over 6 is the x-coordinate of this point. And that's actually a negative x-coordinate. It's negative root 3 over 2. And sine of 5 pi over 6 is the y-coordinate of this point, which you read off immediately as being 1/2. So we were able to compute trigonometric functions, sine and cosine, of a lot of different angles here. And you should try some of these and get fluent at it. Anytime you have a multiple of 45 degrees, 60 degrees, or 30 degrees, you should be able to work out that trig function using the unit circle from these two triangles. Now, granted, there are going to be a lot of other angles that are different from these that maybe you might have to trot out your calculator to work out. Be sure it's in radian mode, and you should be able to work out sine and cosine of any angle with a calculator. However, again, don't rely too much on your calculator. Because if you rely too much on it, it's sort of like using GPS to get around all the time. You really don't know your way around. It's the same with trig functions. If you rely on a calculator, you really don't know your way around trig functions, and you forget about what they are. Also, in calculus, it's going to be a fact in Calculus 1, so many times in problems, what's being plugged into sine and cosine is something that you can find with these two triangles. So get some practice, get good at it, it'll pay off. Next, I want to talk about graphs of sine and cosine. They have interesting graphs. First, the graph of sine of theta. It goes up and down and oscillates as indicated here. And think about how that makes sense. As the the unit circle is just for reference here, as you go from 0 radians to pi over 2 radians to pi radians, sine increases from 0 y-coordinate to a y-coordinate of 1 at pi over 2 to a y-coordinate of 0 at pi. And you see the graph of sine of theta going from 0, and then it reaches a height of 1 at pi over 2. And by the time you get to theta equals pi, you're back down to 0. Continuing along past pi, that y-coordinate becomes negative, down to a y-coordinate of -1 at 3 pi over 2. So the function dips down like this. And then it continues as you go around and around the unit circle, increasing a radian measure of theta. Those y-coordinates grow to 1, shrink to 0, go down to -1, shrink to 0, go to 1, shrink to 0, go to -1, back up to 0. It gives you a graph that goes up and down, as indicated here. It's called a sine wave. Notice it never gets beyond 1, nor does it get below -1. For the graph of cosine of theta, we could do the same thing. Here's a reference unit circle. As theta goes from 0 radians to pi over 2 radians to pi radians, cosine being the x-coordinate starts out at 1, right here when you have theta equals 0, 1. That's the x-coordinate at this point. And as theta increases to pi over 2, that x-coordinate shrinks to 0. So the graph goes from a height of 1 down to a height of 0 at pi over 2. Going past pi over 2, those x-coordinates become negative. So you dip down below in negative realm. And continuing around the unit circle, increasing those radians forever counterclockwise, gives you a graph that oscillates up and down. Here are sine and cosine graphed together, and you'll notice here that the graph of cosine of theta is exactly the same as the graph of sine theta, but moved over pi over 2 units to the left. And if you think about what you know about shifting graphs, that means that cosine theta equals sine of theta plus pi over 2, shifting the graph of sine pi over 2 units to the left. And this is an equation or identity that holds for all values of theta, which you should read about in your text. There are actually 6 trigonometric functions. We've talked about sine and cosine so far today. Now the other 4 trig functions are each expressible in terms of sine and cosine. There's a trig function called secant theta that by definition equals 1 over cosine theta. Cosecant theta equals 1 over sine theta. Tangent theta is sine theta over cosine theta. And cotangent theta is cosine theta over sine theta. These are the 6 basic trigonometric functions. And again, this is just a quick review. You should have some experience with these already. Let's just do one quick example. Imagine you needed to compute tangent of pi over 6. Well, that's sine of pi over 6 divided by cosine pi over 6 by definition of tangent. And to do this, you might want to look at the unit circle to reference pi over 6. Pi over 6 radians is 30 degrees, and you get this 30, 60, 90 triangle. And from it, you recognize that the shorter side is 1/2. The horizontal side is square root of 3 over 2. So sine of pi over 6 is 1/2. Cosine pi over 6 is square root of 3 over 2. Simplifying, we get 1 over square root of 3. Let's now talk about some graphs of these other 4 trigonometric functions. We'll start with the graph of secant theta. Secant theta is 1 over cosine theta. And because it involves a cosine, it's reasonable to start with the graph of y equals cosine of theta, drawn dotted. Now, of course, that's not the graph we're interested in. We want to graph the reciprocal of that. Now, if you think about 1 over cosine theta, when theta is 0, cosine of 0 is 1. Right here, the reciprocal of 1 is 1. So the graph of secant theta passes through this point. But as theta approaches pi over 2, cosine of theta gets closer and closer to 0. So this reciprocal would be getting bigger and bigger and bigger. So you'd expect the graph of secant theta to move up like this. And in fact, it does. Here's its graph. For cosecant theta, it's 1 over sine theta. To draw its graph, we'll start with the graph of sine of theta here. And let's see, when theta is close to 0 or close to pi, sine of theta is going to be very close to 0, so that reciprocal is going to be very large. But when theta is pi over 2, sine of pi over 2 is 1, so the reciprocal of 1 is 1. So the graph is going to go through this point. So you'd expect it to look like a U shape coming through like that, getting very large when x is close to 0 or pi. And in fact, that's exactly what it looks like. So this is the graph of cosecant theta. And we're being kind of brief here. You should review this and think about it and make sure that the graph that I've shown here really does make sense, given the definition of cosecant. Comparing the graphs of secant and cosecant, you'll notice that the graph of cosecant is the graph of secant moved over pi over 2 units. So shifting graphs would tell us that cosecant theta is secant theta minus pi over 2. So we have this basic identity relating the two graphs, the two functions, secant and cosecant. For the graph of tangent theta, it's sine theta over cosine theta. So thinking about this, if theta is 0, sine of 0 is 0, cosine of 0 is 1, so we get 0 divided by 1. Tangent of 0 equals 0. So the graph passes through this point right here. Now as x gets closer and closer to pi over 2, sine of theta gets closer and closer to 1, but cosine theta gets closer and closer to 0. So this fraction, this ratio, is going to get bigger and bigger and bigger as the bottom gets closer and closer to 0. So the graph of tangent goes up to infinity, and you get a vertical asymptote right here at pi over 2. And that same pattern is repeated in multiples of pi. Moving on to the graph of cotangent theta. Cotangent theta is cosine theta over sine theta. It's the reciprocal of tangent theta. So when tangent theta is close to 0, cotangent theta will be close to infinity. And when tangent of theta is very, very large, cotangent of theta will be very, very small. So we're going to get a graph that looks something like this. And again, I'm being a little bit brief here. You should take some time, think about this, study your text, and convince yourself that these graphs really are as they should be. We'll note one thing about the comparison of tangent and cotangent. If you look carefully at the corresponding graphs, there's a relationship between the two. If you reflected the graph of y equals tangent of x, of theta, over the x-axis, it would flip over like this, and that would be the graph of cotangent moved over pi over 2 units to the left. So in terms of shifting graphs, we get a relationship between these two functions. Cotangent of theta is equal to negative tangent. of theta minus pi over 2. So that's it for today. You should read your text carefully. Make sure you understand these functions. We're not quite done with our trig review. Coming up in lecture 3b, we'll talk about solving triangles, trigonometric identities, and solving trigonometric equations. Now, between now and then, it's very important to work some practice exercises. If you feel at all rusty, just check your skills with this. Do that, and I'll see you next time. Goodbye.